In this video, we'll talk about similar triangles and how they relate to similar polygons and how they differ from similar polygons. So it turns out with triangles that we don't need quite as much information to guarantee similarity. And again, this only applies to triangles, and this is where some of the confusion with similar polygons stems from. So the first case, which probably causes the most confusion with the polygons, is what's called angle-angle similarity. Now these are kind of similar to triangle congruency theorems. So if we're looking at two triangles, where on one triangle I know two different angles, and then another triangle has pairwise the same two angles. Well, it turns out, and we know this by third angle theorem, that two angles is enough to get me the third. And it turns out for a triangle that if three angles are congruent, if three angles are congruent, then I'm guaranteed similarity, just because there's no other way to form that triangle with those three angles. Those side lengths have to be made proportional, and that's kind of where we have a lot of textbooks will call this a postulate kind of thing. But many textbooks will call it the either three-angle similarity or a double-angle similarity, since two angles is enough to get me the third. So if you know two pairs of angles are congruent, you can say the triangles are congruent. Likewise, if we look at what's called the side-side-side similarity, and for this one I'm going to label these above triangles here. Let's say I have side A, side B, side C, and then I have X, Y, and Z. Now I'm just labeling them as single letters for the sake of simplicity here. If I know all three sides of the triangle and I know that all three, proportionally speaking, are the same, so in this case we're looking at corresponding or like sides. So if A over X is equivalent to B over Y and C over Z, then I can deduce the triangles are similar. And I suppose this one goes both ways. If I know they're similar, then yes, I know the side lengths are proportional. I'm given that. And then there's one more special case called the side-angle-side similarity. And this one, I'll draw a separate case just to kind of iterate the point. But basically, if I know, it's kind of a combination of these two top ones that we have here. If we know one angle is congruent, and we also know that these side lengths are proportional, meaning, let's say I have 5 over 10 or 5 and 10 on the left triangle, and I know this one is half the size, so we're looking at 2.5 and 5. If these are proportional, these two side lengths, and the angles are congruent, then I know that the triangles are congruent, or similar, not congruent. So it's worth noting, this kind of is a very special, very seldomly used case. Oftentimes we're looking at the angle-angle similarity is the most popular, and failing that, the side-side-side usually is useful. But this one does pop up from time to time, so it's worth being aware of. So let's walk through an example of where we would use this. So you see this a lot when you're talking about blueprints or expanding something or just simply extending the sides of a triangle like we kind of have here. So what I'm given is I want to solve for x, and something that's worth noting is that these two side lengths that I'm going to highlight in blue are parallel to each other. That's what this little blue arrow is useful for. So what that does for me is it makes it to where I don't necessarily know what these angles are, but I do know that they are congruent. And that makes it technically to where I know these angles are congruent. So in this case, I am looking at angle-angle similarity or angle-angle-angle similarity, since I do know they share this 24-degree angle. So this guarantees me that these triangles are indeed similar. So with that in mind, I know that the side lengths have to be proportional. So if I'm looking at two different triangles here, I'll draw the big one in green. So I'm looking at the big triangle. I know that when I take these two side lengths 26 over 12, and I've just got to be very careful with my order here. 26 is a bottom side, so I have to make sure I compare that to another bottom side, which I know that's 7, because I'm looking at this little triangle here, which I'll draw in red. So I'm going to have 7, which is the bottom side of the small triangle, divided by the kind of slant side of that triangle, which is x. And at this point, I can cross multiply to try and solve for x. So then I know 26x is going to equal 7 times 12, which is 84. Therefore, x is going to equal 84 divided by 26. And I don't have a calculator handy on me, but we can get a decimal approximation here, and this would essentially be our solution. So, very useful application of similar figures. Mostly we see triangles because triangles are used everywhere. Triangles are a very powerful figure in construction and very solid, very stable, and it's very useful to be able to do these kind of things. And these things just happen to pop up a lot, especially these parallel sides. It's just worth mentioning. So here's one application. A lot of what we'll be doing with this is either finding sides, or we'll just be trying to determine if something is similar or not. So hope this helps.